In this video, we're going to talk about vectors and vector operations. We've already used vectors already in our study of kinematics, but we need to be able to look at them graphically, visually, geometrically when we're dealing with two-dimensional motion, most of which we'll concern ourselves with in terms of projectiles. So, as a reminder, vector quantities of magnitude and direction. We have some examples from kinematics, that's up there. Scalar quantities, just magnitude, some examples. Things we need to know for 2D kinematics and projectiles is how to add and subtract vectors. When you get that result of adding or subtracting vectors, we call that the resultant. We need to be able to break up a resultant vector into its horizontal and vertical parts or components, and that's called resolving a vector. And those parts that are horizontal and vertical are going to be parallel to the x and y axes respectively. So the horizontal component is going to be parallel to the x-axis, the vertical component parallel to the y-axis. And that's real convenient because the x and y axes are perpendicular to each other. So we like to keep our vector components perpendicular if possible. And we also need to use the horizontal and vertical components of a vector to determine its direction. So we'll start with an example just of visualizing vectors. I've got our Nerf gun and dart, just like we used in the exit velocity lab to determine how quickly the dart was leaving the dart gun. I'm going to define my directions real quick. I'm going to say up is positive and down is the negative direction. That's important. And for the sake of argument and make the numbers easier, I'm going to say the exit velocity or initial velocity of the dart is going to be 50 meters per second. Let's start with that. Okay, so generally we know what's going to happen. We launch the dart. Where's the dart? If I grab the dart, we launch it. It has some initial speed of 50. Shoots up. As it's climbing and achieving a higher vertical position, its speed is also dropping. So its velocity in the y or vertical direction is decreasing in magnitude because of the gravitational acceleration in the opposite direction. It gets to its maximum height and stops, and then it picks up speed, and now its velocity is in the negative direction and increasing in magnitude because little g is still always pointing down. So we're going to map that out. The first vector, let's draw it in purple, will be our gravitational acceleration, little g. We know that's always going to be pointing towards the center of the Earth or to the ground. And so that vector there, the length, indicates magnitude or how much. And the arrow indicates direction. What direction does that vector point in? So those are the two pieces of the visual arrow that represents a vector quantity. In this case, this is little g because it's pointing down, and we call down the negative direction. It is minus 10 meters per second squared, okay? Or minus 9.8 if you like. So that's one vector that's present here, and I'll keep that in purple. We also have initial velocity, and then we also have a velocity that's changing as the thing flies up into the air. So we'll do a little table quickly over here, because some people approach solving problems on the test with a table. So we could do that. Let's say we have a table with time, velocity, and position. And let's say we have 0 seconds, 1, 2, 3, 4, 5. And our velocities we know at 0 seconds, that's when it's leaving the barrel of the Nerf gun, 50 meters per second. What happens every second? Well, it's moving against the gravitational acceleration. We know it's slowing down, and it loses 10 meters per second of speed every second. So after 1 second, it's got 40 meters per second. After 2, 30. After 3 seconds, 20. 4 seconds, only 10. And after 5, it has 0 velocity, and that's when it reached its highest point. For positions of where this thing is going to be, you can see I have a scale over here up to 130 meters for us to mark its positions. When you think about what's the initial position, well, that's 0. And its final position, which we'll just call y, is going to be given by this equation if we'd like to use it. I'm going to call velocity initial in the y direction. It's time. And since we're calling down negative, I'll use minus 1/2 gt squared. And so this can tell us our displacement or final position for our Nerf dart, let's say at t equals 1 second. Well, let's think this equation. We know initial velocity is 50, so this is 50t minus 1/2 g. Well, if g is 10, then 1/2 of that is 5, so this is minus 5t squared. That's what we can use to find our position. So after 1 second, 50 times 1 is 1, minus 5 is 45, and that'll be meters. And t equals 2 seconds, we'll have 50 times 2 is 100, minus 20, so we'll have 80 meters. At 3 seconds, we're going to have 150 minus 45, so it'll be at 105 meters. Just substituting the value of time to see what our positions are going to be. At 4 seconds, I have 200 minus 80, so 120 meters. And at t equals 5 seconds, we'll have 5 times 50 is 250, minus 5 times 25 is 125. So it'll be at a position of 125 meters. Not apparently clear, or obvious, I would say, that our positions are going to be 45, 80, 105, 120. So be careful making a table. Make sure you're actually calculating it properly. We go back to our table. At t equals 0, the position is 0. And then we have 45, 80, 105, 120, and its maximum height 125. And this is position in meters, velocity in meters per second, and time in seconds. Okay, just as a side note, check out these differences. 45 to 80 is a difference of 35. 80 to 105 is a difference of 25. 105 to 120 is a difference of 15. See in the pattern? All right. And then look at the differences between those. All right, so that's because we have accelerated motion. Our position is not changing at a constant rate. It's curvy, quadratic. All right, so now we know all the positions of this dart. Let's just mark them. At 1 second, we were at 45. So let's say we launch from here. We get 45 is right there. At 2 seconds, we're at 80, I think. And then we're at 105, 3, 4 seconds, we're at 120, and at 5 seconds, we're at 125. Did I do that right? Let's check the table. 80, 105, 120, 125. Okay, and then at 0 seconds, we're way down here. That's the starting point. Okay? All right, so there are positions. That's y initial. And then all of those dots, it just looks like the dot diagram that we discussed at the very beginning. The dots are getting closer together because the dart on the way up is slowing down. Okay, so we have a table to help us find our positions. And remember, always when you get to looking for maximum height, you can use this guy right here. Final velocity at maximum height is 0. Initial velocity is 50 minus gt. So you get our time from that, and you can also use this one, v final squared equals v initial squared minus 2g delta y to get your final position or total displacement if you know final velocity is 0 at the maximum height. All right, so now we're going to mark in the velocity vectors, what those arrows actually look like. I'm going to do them in pink, I think. So there we go. Shape, arrow. All right, so initially, let's use every grid, every block will represent 10 meters per second. Because remember, the length of my arrow represents the magnitude. So we start with 50 meters per second. So in our first dot, we're going to go up 1, 2, 3, 4, 5. All right, so that's 50 meters per second, right? 1, 2, 3, 4, 5. Yeah, I think I counted right. So at the next second, we have an upward velocity, positive, 40. 1, 2, 3, 4. And then we have 30, 20, and 10, and 0. So here's 3 for 30, 20. The direction of the arrow matters, tells me the direction it's moving, and the length matters, it shows me the amount. There's 10, and then at our very tippity top, there's no velocity vector to put on that last dot because the velocity right there is 0. So this last dot, v in the y direction, is 0, so I have no arrow to draw. Right here, vy is positive 10. Here, vy is our 20. So this is how we use our arrows to help represent what those vector quantities are. So pink is our velocity, blue is our position, and purple is our gravitational acceleration. And we could even draw, if we wanted to find a displacement vector, let's say delta y is y final minus y initial. It's a vector. And let's say I want to go from 0 seconds to 2 seconds. Well, this was the position at 0 seconds, and at 1, 2, the position's up here. I'm just drawing it to the side so we see it without covering up our other arrows. Then we would have a nice blue vector arrow for displacement going from, notice the tail goes from where we start and the arrow points to where we end up. That arrow is important which way it faces because it tells us our direction for that vector. So in this case, from 0 to 2 seconds, my delta y is a positive 80, and I can represent that with the length of the arrow going from 0 to 80. That's 80 meters, and the arrow points upwards, indicating a positive displacement. All right. All my velocity vector arrows point upward, indicating positive velocities. So there's where we can represent our motion at different stages in time with our vector arrows. Okay, so we have a way to represent vectors at different points in time. Now we want to be able to combine them or take them down into their basic parts and also find their directions. This is a pretty easy direction to state. We could say the direction of our launch velocity, for instance, is up, or you could say that its direction is 90 degrees, since we measure our angles by default from the positive x-axis. So we'd be measuring that angle from positive x up to that launch angle. Would be 90 degrees. So there's one way you could give the direction, or in this case we could just say positive y. So adding and subtracting vectors. In the notes you'll see part of this, which is when adding vectors graphically, we always place the tail of the second vector on the arrowhead of the first one, and if they're parallel or anti-parallel, so basically if they're both along the x-axis like these guys, yeah, it's really easy just to add them arithmetically, you get 10. If the one in one direction, one in the other direction, you use the minus sign to indicate it's in the other direction. You add those arithmetically, you get 0. Same thing if you have them both in the vertical direction. You'd add them tail of the second one to the arrowhead of the first, draw the remainder from the exposed tail to the exposed arrow, and you add them just arithmetically because they're already in the same direction. No problems there. When we have them and they're not parallel, we want them to be perpendicular because that makes it easier. So when they're not parallel, like these guys here, vectors A and B are perpendicular, we use the same method, but you can't just add their values to get the total resultant vector's magnitude. For instance, here, they're perpendicular, so this is a right angle. This is vector A, it's literally copy-pasted from over here. And then we take vector B and we place the tail onto the arrow of A, so this is vector B, and A plus B is the blue resultant vector that's drawn. So we call that blue vector A plus B, and it equals the resultant, which we sometimes call R. And there it is. How do we get the magnitude of R? Now that's something we need to be able to do if we're adding vectors that are not parallel, because we can't just add up the value of A and B. For instance, if A's magnitude is 3, and B's, which it doesn't look like, but let's just say, and B's magnitude is 4, the resultant vector's value of its magnitude is not 7. We can't just add 3 plus 4 is 7. We have to use the Pythagorean theorem. And so to do that, here we would have r squared, let's call r the resultant vector, the magnitude of the resultant vector, not its direction, it's its magnitude. R squared equals the magnitude of A squared plus the magnitude of B squared. So the magnitude of R is square root magnitude A squared plus magnitude B squared. All right, so this one pretty easy. We get 3 squared, it's 9 plus 4 squared is 9 plus 16 is 25. Square root of that is 5. So this is a 3, 4, 5 triangle. So the magnitude is 5, whatever the units are. And so that would be my magnitude of the resultant vector would be 5, whatever units. So that's what we have to use when they are not parallel to each other. If it's not a right triangle, then you're going to have to either build other little right triangles out of the other vectors or use law of sines or law of cosines. We don't really want to have to do that. We always want to keep them perpendicular so we get right triangles. So Pythagorean theorem, that's what we can use to add. All right, so that's number 1 up there in the first bullet, adding, subtracting vectors, either arithmetically or with Pythagorean theorem. Check. Break up a resultant vector into its horizontal and vertical parts or components. So let's take our example of, this guy's back, of the Nerf gun launcher. So let me do what I did before and call up positive and down negative. And I'm not going to make a whole table here. We're just going to do a little geometry. I am going to draw an x-axis. This time notice that the Nerf gun is launching. I'm going to make, well, I guess this will be the x-axis because that's where the barrel is. Doot, doot. And then we have a y-axis. Put it right there. And this thing was launched at about 30 degrees. You can see that. All right, so here's an example of having a direction involved that's not strictly parallel to the y or x axis. It's somewhere in between. And that's where we have to deal with two-dimensional motion, including our vectors. So this dart's been launched. It's going to go flying, right? And then it's going to come back down. And that path that it travels in, we call a trajectory. That's good to know. And for our projectiles, the trajectory is going to be parabolic because we are not going to deal with any other forces but gravity acting on them, pretty much. So that means we get nice parabolic trajectories. All right, so that's the path that it's going to travel. Notice it's going to move a horizontal distance, like this far, but it's also going to move a vertical distance. It might have 0 vertical displacement if it comes back to the same y position, but its x position has changed, and all the while during its flight, its velocity is changing in both directions, and so we got some stuff to deal with. So let's say one vector we can draw. Let's do launch velocity again. Let's say its launch velocity was 50 meters a second. Call it v initial, and I can draw my little arrow. We'll draw it right here from the barrel in 30-ish degrees, but I want it to be nice and long so we can draw on it. So that doesn't look like 30 degrees, but whatever. That's fine. Let's say that's close enough. All right, so here's v initial is 50 meters per second. All right, so imagine in your mind now, what two vectors could we add together to make this 50 meter per second diagonal vector? And we want them to be along or parallel to the y and the x axes. So I'll do, let's say blue. Blue is going to represent our x axis or x component. Use this light blue. And I'm going to go from where the tail is of my vector. And this is basically showing our, just like your final x coordinate. Like how far does this arrow, if you're considering like the slope and its initial positions at the origin, how far to the right do you have to move and how far up do you have to move to get to the arrowhead? So this is like the x final coordinate right here where my blue arrow ends. And then let's make our green can be our y component. Wait, no, you stay that color. And then I want a new one. That's green. Yes, thank you. My goodness. All right, so then our y component must go like this. All right, it looks like the picture in the notes from before, does it not? Here you have a right triangle. We know the hypotenuse. There's a right triangle. We know it's a right triangle because we've drawn these vectors along the x-axis and parallel to the y-axis, and the x and y-axes are perpendicular. At least that green one's supposed to be perpendicular. Okay, there it is. So we call this component down here in blue the initial velocity in the x direction. Because it's the initial velocity, but only part of it. And it's only the blue part, the horizontal part. And then we call our vertical part VIY, the initial velocity in the y direction. And we want to be able to figure out what VIX and VIY are. And what we need in order to do that is the hypotenuse of this right triangle, which we have, but we also need the launch angle. There's the launch angle. We're going to call our angles by Greek letters, so this guy's theta. Why not? And I'm going to go ahead and say that it's launched at 30 degrees. That's something we know. So the question now is, how do we find VIX and VIY? Fortunately, it's just the simplest of trigonometry, and this is why we want to keep our right triangles and not really use any other crazy triangles. I know that my useful trig functions sine of an angle, cosine of an angle, and tangent of an angle can be used to help me find the other sides of a right angle triangle, or to work backwards and find angles or find the hypotenuse or whatever you want. So remember that our sine is the relationship or ratio of opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. Okay? So if we want to find VIX, and I know the hypotenuse and I know the angle, I need to first ask, what is the relationship in terms of its position, VIX, to the angle? Is it adjacent or opposite? And VIX is adjacent. So that tells me that for blue, I want to use cosine. And I look at green and I say, is that opposite or adjacent the angle? It's opposite. It's way over there. That's what opposite means. So sine is going to be a useful function for determining the value of VIY. So usually we have the hypotenuse and the angle, so we're usually using sine or cosine. So let's do VIX first. I know the cosine of this angle, 30 degrees, is going to be equal to the adjacent side, which is my VIX, divided by my initial velocity VI, or my hypotenuse. Rearrange it to solve for VIX, or the horizontal component of the initial velocity. I have VI cosine 30 degrees equals VIX. So we'll have hypotenuse times the cosine of the angle is going to get us our horizontal component. That's what we need to know. Now we know VI is 50, and the cosine of 30 degrees is square root 3 over 2. All right, so that's equal to VIX, or we could just say 25 square roots of 3 equals VIX, and then we can get an actual value, which we might want to do. So when we're using our calculators, make sure that you are on degree mode if we're using degrees. So let's check. Okay, we're on degree mode. Cool. And then we want quit. We want 25 square roots of 3, 25 square root 3 is 43.3. Okay, and if I do just 50, if I use the cosine function there, 50 cosine, what did I say, 30? 43.3. Okay, so square root 3 over 2 is the cosine of 30, and our value for this guy is 43.3. All right, so we're going to write it in pink, 43.3. Oh, let's do it in blue because it's our blue component. And that's units are meters per second because that vector is a velocity vector. So our horizontal component is 43.3 meters per second. Okay, we can do a similar thing for our vertical component in green. We said sine function is going to be the one that's relevant since the side is opposite the angle. So we're going to say sine 30 degrees equals VI, the opposite side, VIY, over our hypotenuse, which is the initial velocity. Rearrange it, solve for what we want. So VI sine 30 is VIY, the initial velocity is vertical or y component. And then we just need to solve. Sine 30 is 1/2, so I have 50 times 1/2. That's going to be equal to our initial velocity in the y direction, or 25 meters per second. Keep it in green. Is VIY. Okay. All right, so now we've gotten both vertical and horizontal components of our initial velocity vector. That's called resolving or breaking down a vector into its component parts. We always want those component parts to be parallel to the x and y axes, because if they're parallel to the x and y axes, they will be perpendicular to each other. And we want to have perpendicular or right-angled triangles so that we can just use our nice trig functions simply without doing any other messier trick. All right, we can also check this with our Pythagorean theorem, because we know if we have 43.3 and 25 as the sides that are not the hypotenuse, then we should be able to use Pythagorean theorem to show that they produce 50 for the value of the hypotenuse. So let's do square root 43.3 squared, which is a rounded value, so it won't be exactly 50. 25 squared. And we get 49.9950. Okay? All right, so Pythagorean theorem gets us back to the hypotenuse. We can use sine and cosine functions to get our other sides. You can also use the tangent function if you knew like the horizontal component and you wanted to find the vertical component, then you can use tangent 30 is the opposite side over that adjacent side you know the value of, and calculate what the missing side is that you need to know. All right. So there's 2. Second bullet is checked off. We can break up a resultant vector into its horizontal and vertical parts or components. The last one is to use the horizontal and vertical components of a vector to determine its direction. So this guy only has one part to it. It's all vertical. So the direction is very easy to determine. If everything's vertical, it's 90 degrees, or it's going to be minus 90 degrees. If everything's horizontal, then like if it's launched horizontally off the edge of a table, then the angle is 0 degrees, or you could say 180 degrees or minus 180 degrees, depending on what direction you're calling the 0 degree direction. But when we are at something like this is going on, we need to make sure that we can figure out what the angle is. Okay, so let's just replicate this scenario here. We're going to take a big snapshot of that and hope it works. And then I'm going to remove, let's make it a little bigger, why not? And then I'm going to remove this guy and the angle, and we'll make up some new values for these guys. Okay, so let's say that we know that the initial velocity in the x direction is 30 meters per second, and we know that that's not going to be to scale. Let's say we know the initial velocity in the x direction is going to be 40 meters per second, and the initial velocity in the y direction is 30 meters per second. Now the pink vector there, that's the true full velocity still. That's still the full VI, but we maybe don't know or don't really have the time to do the Pythagorean theorem and figure it out because we don't care and we just want the angle. I mean, we know that's going to be 50, right? But let's say we have no interest in determining that hypotenuse. We just want to, as quickly as possible, figure out the angle. Theta, the launch angle, is question mark. Okay, well, what we can do is we can look at what sides we have. According to that angle I have over there, the opposite side. That's one value I know. And right next to it, I also know the adjacent side. Okay, so then I look at my trig functions, sine, theta, cosine theta, tangent theta, and I think about which one is relevant. So this was opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Aha, okay, tangent, right? Because I have the opposite side from the angle in green, and I have the adjacent side in blue, because we don't know our pink value right now. So I can use the tangent function here because it has the relevant sides. When we're looking for the angle, So let's say tangent theta is, let's call it y component over x component. When I'm looking for the angle, we use the arctangent function, or the arc sine, or the arc cosine, because it gets you the degrees of arc. So my arctangent function is, same button on your calculator, tangent minus 1 of this relationship, y or opposite over x or adjacent, is equal to the angle. And usually I'll write it, if I'm solving for the angle, this is the same thing, I'm just writing it the other way. The angle I want is arctan y over x. Okay. Or inverse tangent, some people call it, but it's not the reciprocal, so just be careful. It's the arctangent. Okay, so in this case, we have our angle theta that we want to find. We know that our tangent function relates the opposite to the adjacent side. So for us, we have on the opposite side, we have in green 30 meters per second over our adjacent side is 40 meters per second. And so our angle should be, I have no idea, probably like 37 or something. So we need to calculate what the arctangent's result's going to be. So notice I have tangent button, usually it's second tangent button, or second cosine, or second sine, that'll get you the arc function. So there is arctangent 30 over 40, come on, is 36 point, wow, that was a good guess. So 36.87, let's call it 36.9. All right, so that's the value of our angle. All we need are 2 of the sides, and we're good to roll. Sometimes you might know the hypotenuse and then like the vertical component, and you can figure out the angle. A lot of the time, though, what we have are the 2 component parts, the x component, the y component, so the arctangent is going to be the one that we'll mostly use to solve it most quickly. What else do we got? 36.9 degrees. One important thing to mention here is like, if these component parts were equal, like if this were 40 meters per second and this were 40 meters per second also, then we would have an initial velocity that was like that, and the angle would have to be 45 degrees. So you know if the 2 values are the same, the x component, y component are equal, the angle or the direction is 45 degrees. If the y component is smaller than 45 degrees, like we have here, the y component is not smaller than 45 degrees, the y component is smaller than the x component, then we'll have an angle that's less than 45. You can imagine if the y component is larger than the x component, then you're going to have an angle that's more than 45 degrees. So there's an important thing is to bear in mind to make sure that your result makes sense. So we have a y component that's shorter, so we should have a smaller angle, less than 45 degrees, and we have 36.9. So that fits, that makes sense. So that's our third thing, being able to find the angle, which is the direction that a vector has given the component parts in the x and y direction. And those are our 3 things. I don't think there was anything else. There's use horizontal and vertical components of vector to determine its direction. All right, that's the stuff. We'll be working problems with vectors and then projectiles and start doing projectile labs this week. Come with questions.